Now we're going to talk about binary numbers. And first of all, you've probably heard of bits and bytes in reference to computers. Now, a bit is the smallest unit that can be represented in a computer. Everything in a computer has either a state of 0 or a state of 1. You could think of it as on or off. You could think of it as a low voltage versus a high voltage, but that's how everything is represented inside a computer. So it all basically boils down to binary numbers, because binary numbers, or base 2 numbers, have two possible values, either a 0 or 1. Just like we use base 10. Base 10 has every place, when you talk about place value, or the ones place, or the tens place, or the hundreds place, in base 10 has 9 possible values. 10 possible values, 0 through 9. So binary numbers have two possible values, 0 through 1, so 0 or 1. When we do base 10, the lowest place, the ones place, is 10 to the 0, because anything to the 0 power is 1. In base 2, or the binary, 2 to the 0 is 1. So this would be equivalent to the ones place. The next place in base 10 is the tens place. The next place in base 2, or binary, is the twos place, 2 to the 1. So this can be, these are ones. This tells how many ones you're using. This tells how many twos we're using. The next place in base 10 is 10 squared, or the hundreds place. The next place in base 2 is 2 squared, which is 4. So this will show you how many ones we need. This will show you how many twos we need. This will show how many fours. How many eights? The next place is 2 to the third, just like the next place in base 10 is 10 to the third, or thousands, and so on. So this is how everything is represented inside a computer using binary or base 2. And it's the same concept as base 10, but everything's based on 2 to the 0 place, 2 to the first place, 2 to the second place, 2 to the third place. Okay, and I did mention about bits. Bytes are just a collection of bits, and they also tend to be in lengths that are numbers that happen to be places within binary. So normally a byte would have 8 bits in it. Sometimes what they call a word in a computer may have 16 bits, it may have 64 bits. So everything is based on those binary values, the place values for base 2. Okay, so how would we represent the number 255 here? Well, that's if everything is turned on here. If I have 0 through 7, this is 2 to the 7th, this is 2 to the 0. So I have basically 8 places here. So the highest number I can represent here is 255, because if I have a 1 here, if I turn on everything, that's like if I had all 9s, if I had, in base 10, if I had, suppose I had 9 places, 9 place values or whatever, and every one of them had the highest possible value, which is a 9 in base 10. That's the highest number I could represent with that many places. Well, in base 2, if I have 8 places, 1, 2, 3, 4, okay, up to 2 to the 0, 2 to the 7th, I can represent, the highest number I can represent with that is if I turn them all on, I give them the highest possible value of 1, add them all up, I get 255. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. Okay, how would I figure out what this binary number represents? Well, again, 2 to the 0, this is the 1's place, 2's place, 4 place, 8 place, 16th place, 32's or 32's place, 64's place, and 128. So add them up, I got a 128. I have no 64's, no 32's, I have a 16. I have no 8's. I have 1 4. I have no 1's. No 2's, and 1 1. Add them all together, you get 149. So we'll practice with that a little bit, but it's good to know what that is, because it makes it easier for you to understand kind of what's going on inside the computer, the hardware. This statement, binary, is easy as 1 2 3. Remember, 1 is just 1. I'm talking about in binary, the 1's place, 2 to the 0. I want one of those, so I want 1 1. That's a 1. So 1 0 would be none of these and one of these. So 2 plus 0. I remember I didn't want any of these. That's 1 2. This one's a 2. So that's 1. That's 2. This one's going to be a 3 because I have 1 in the 1's place, 1 in the 2's place. 2 plus 1 is 3. So binary is easy as 1 1 0 1 1. Okay, now interestingly, to convert a decimal number to binary, all you have to keep doing is dividing by 2 and keep the remainders. and kind of magically it gives you the binary representation. And it comes out nicely if you keep doing this division and take the remainder. Right here I did the division, and I'm taking the remainder. The remainder after division by 2 would be the modulus operator. If I print it out after the recursive call, remember in that case I get the count up, like we did in the previous lesson. Remember count down versus count up. If I do a count up, meaning I print out after I do the recursive call, I will get the numbers printed out in the reverse order of what the function calls were. So what I want, and that's exactly what I want to do when I do this simple conversion to binary. So I start out with the number 23, I divide it by 2, I get 11, the remainder is 1. That should be the ones place. Now I'm calling the same number, the same function, or the same method with a value of 11. 11 divided by 2 is 5, remainder is 1. That will be the twos place in my answer. See, that'll be the twos place down here. Now I call display binary with 5. 5 divided by 2 is 2, remainder 1. This is what I'm interested in, the remainders. That's the fours place. Here's the ones place, twos place, fours place. So this will be the fours place, the third number there. Okay, now I call the same thing. I call display binary with 2. I divide by 2, I get a remainder of 0. That's the eights place. So I have ones place, twos place, fours place, eights place, and then the last one is what do we get up to? So ones place, twos place, fours place, eights place, and 16s place. Okay, so that'll be the 16s place. Remainder is 1 when I divide again by 2. So if I print this out in reverse order, which is exactly what happens when you do recursion, printing out after the function call. That was the count up function. Remember, we're doing the same thing. I get my binary conversion printed out in the right order. So now we'll take a quick look at the binary printout that we had previously in the previous lesson, but I had it commented out because I didn't want to look at it yet. So I commented out the countdown and count up code because we looked at that in the previous lesson, but we want to look at display binary now, which is basically the same thing as count up. It's the same thing as the count up recursive function, except I do division by 2 and I save the remainder, and that's what I'm printing out. So what we'll see is first we're printing out the binary value of 23. That's just what we had before in the example we just looked at. What if I change this to, let's change it to something we know. If I want to print out the binary value of 8, it should be, remember, the first one is the zeros place, the twos place, the fours place, and then the eights place. That's what the binary place values are. So this should really print out the answer 1 with 3 zeros after it. It should be like 1,000, kind of, or 1. It should be 1000. We don't really say 1,000 because that's decimal. So let's see what happens here if I run this. Okay, so it's exactly what we expected. 1 in the eights place, nothing in the the 4, 2, or 1's place. If we put 16 here, let's do a 16 here, we should get a 1 with 4 zeros after it. So let's try that one. Which makes sense because the 16th place is the 5th place. I don't have any 8s, I don't have any 4s, I don't have any 2s, I don't have any 1s. If we print out 17, that should be 1, 0, 0, 1. Because I have a 16 and a 1 is 17. So let's see what happens there. And there it is.